So I'm a bit surprised to see you here again, Brady. I thought we discussed this 2 years ago.
Is that your time travel joke?
Yeah. And it's before the announcement of the event, right?
Right.
The announcement was last week.
Well, something really amazing's happened, basically, because scientists at CERN and in Italy have found that there's a neutrino, which is a certain type of particle, that's actually broken the speed limit. It's gone faster than light.
The terrible jokes are coming because of this recent announcement from this group of experimentalists based in Italy at the Gran Sasso laboratory, who've been doing this an experiment for the past 3 years, where they are looking at neutrinos flying from, being produced in CERN near Geneva, flying through the Italian Alps and landing, going straight through the detectors at Gran Sasso, but some of them are interacting with the detectors.
And so they've got a good idea of what time that neutrino left CERN, and of course they detect at what time it arrived in Gran Sasso. And they know the distance between the two, so they just, from that, they can work out the speed of these things. And they worked out the speed and they found out that it was slightly greater than the speed of light.
Not by very much. The deviation from the speed of light, so if I say take the velocity of the neutrinos, subtract from it the velocity of light, and divide by the velocity of light, so it's got no dimensions, that number's 10 to the minus 5, so it's 1 part in 100,000, so it sounds negligible, and everybody should say, well, okay, so it is the speed of light then, but they believe their statistics are so good that it could well be that it's a real effect.
I mean, you just think how fast these things are going, right? So they're going so quickly. To notice any time difference at all, you know, you've got to sort of have them travel over a very large distance. So, I mean, these things are only, you know, I think they've arrived 60 nanoseconds faster than light would have done. Okay, so that's a tiny, 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 tiny time scale. And yet they still travelled over 730 kilometres.
To be fair to the experimentalists, they themselves are sceptical. I think that you can tell by the fact that the way they've announced the results, the paper that they've put out on the archive for everyone to see, they openly say, this is strange. We don't understand why this result is there, but we've tried everything we can to account for all the errors that might bring it back within the speed of light, so that the neutrinos are going at the speed of light or slightly less, and they can't find any reason why they are.
Okay, so I guess most people's first impression is that, you know, this is almost too incredible to be true, and certainly that's probably true of most scientists. But of course, you know, if something happens, we have to look into it, and actually look very closely at what's gone on. The first thing you might say is, have they got, say, the distance between the source and the detector right? Have they measured it correctly? But they've used very sophisticated GPS, that kind of thing, and it seems that they can get the distance right to within 20 centimetres. So this, taking into account the Earth's rotation, taking into account sort of, movement of the Earth's crust, all this kind of thing, all this has gone into it to work out this distance very, very, very precisely. And actually, the consensus does seem to be that the distance calculation is right, that there's really nothing wrong there. There's slightly more, there's many more concerns really regarding the time. Okay, so again, they have to measure the time of departure and the time of arrival, and they have to measure it very accurately. Now they claim they can get the time of flight accurate to within about 10 nanoseconds, and given that the time difference is 60 nanoseconds, they're like, okay, that's good enough.
And so they've basically put it out to the community. They've pleaded for another experiment to be done. And as it happens, there are 2 experiments that could be done to test this, both also firing neutrinos long distances. And that's, I suppose, the plan now, that these 2 experiments which are already underway, will try and home in on this particular result.
Let's just assume it's true, right? I mean, it's more exciting if it is, right? So, what's going on? Okay, well, you've got to really understand sort of quite how groundbreaking this is. Now, in Einstein's relativity, the speed of light is the maximum speed that any normal particle can go at. You can't accelerate beyond the speed of light. And the reason you can't is as you approach the speed of light, your mass becomes infinite, and so you need an infinite amount of energy to go beyond that speed. That's true of most particles, right? There is a certain type of particle which can go beyond the speed of light. It's called a tachyon. You may have heard that word sort of touted around in the last week. Basically, this is a particle whose mass is actually imaginary. So if it's got imaginary mass, that means that like an imaginary number is something like the square root of -1 or the square root of -2. So this is a mass which is the square root of something negative. So these are very peculiar particles. In any sort of quantum theory, we normally associate them with horrendous instability. So we don't like them. But if you're prepared to accept that they might exist, then they would travel faster than light, but with very profound consequences, actually. One of the consequences is that you could potentially send signals back in time. So one possibility is that it's a tachyon and that you can send signals back in time and that you can kill your grandfather before you were born and before he was born, and all those paradoxes associated with that. The other possibility, of course, is other exotic things, that there's no such exotic idea of time travel or anything like that, but perhaps this neutrino is passing through an extra dimension. It's taking a shortcut through an extra dimension. So if you like, it's like traveling from London to Australia, but rather than going around the sort of two-dimensional surface of the Earth, you burrow through the center and take a shortcut through the Earth's core. It's kind of like that idea. Another possibility is that the neutrinos are seeing like a different geometry. So the thing that controls the maximum speed is really the geometry of your space-time, okay? So if everything else sees one particular geometry and the neutrino sees another geometry, then the rules of the game for the neutrino are different to the rules of the game for everything else.
I'm a little bit skeptical. I think but I'm a theorist, so I'm very excited. But I think it's time to sit back and look in a lot more detail at their analysis, which is kind of out of my league to do that, but I've read the paper, I've listened to the talk. It's clear from reading the paper, it's a really difficult experiment.
I think that most people's reaction tends to be to dismiss it immediately. Sometimes a bit too readily, I think. I mean, I'm a bit different, and I'm a sort of eternal optimist. So, when these kinds of results come out, I get very excited about it. But, as I said, I'm the eternal optimist. I always start of every season, I think Liverpool are going to win the league. So it probably says something more about me than about my colleagues.
I mean, one of the reasons is because if you don't only think about the particle physics, if you think about the astrophysics, there are other reasons why you'd have to treat this bit of data at the moment with a degree of skepticism. So in astrophysics, we know about supernovae. Okay, now in 1987 a supernovae went off. In fact, I was at Fermilab when the supernovae went off. Well, it had gone off years before, but we detected it. We know that with those supernovae, neutrinos and light arrived within 3 hours of each other. Now, and that's perfectly well understood, because in a supernovae, the neutrinos are emitted as soon as the core collapses, so they begin their journey straight away almost. The light doesn't emit until the shock wave is bounced, and then the light can escape, and there's like a 3-hour difference. And that, assuming they both went at the speed of light, that accounted perfectly for this difference. If this result holds, and it holds for all the neutrinos, then we would have expected to see the burst of neutrinos 3.5 years earlier, because the neutrinos were going that much faster, and there was no evidence of any neutrinos arriving 3.5 years earlier.